So then here's my, So welcome back everybody for this last session. After this session, there will be a feedback session as well as the vote of thanks. And for that, please join the parallel session 1. I think it will begin at 5:15. Let me please check the schedule again. 1 second.
5:06, I think.
5:06, is it?
No.
I have to check what he has. Yeah, it's 5:06. So please join the parallel session 1 for giving feedback especially, and also for the vote of thanks. Yeah. With that, I'll just hand over to Kalpataru Pradhan of SINP to chair the session.
Okay, welcome back. So now we have 3 talks. This is a special session, I guess. One is a 15-minute, one is 30-minute, another talk is 1 hour. So we'll start with 30-minute talk. Amitabh from RMD Educational Institute. So Amitabh, so I'll remind you in 20 minutes. Okay, so we have 30 minutes. So 25 minutes the talk time. So then in 5 minutes for question answer. So I'll remind you in 20 minutes. Okay, should we start now or wait for another minute?
Exactly at, I think, start at 3. Yeah.
Yeah. So let's wait for 1 minute.
Because everybody loves to join in the first 2-3 minutes of the talk.
Yeah. Actually, putting a picture of Matthias somewhere in between would be interesting.
That was Gautam's sheet, I guess, right? I mean,
yeah, we see the 4 pictures, but Matthias would fit somewhere in between.
Amitabh can support it.
With his unconventional statements.
Okay, Amitabh, let's start.
Cameling horns and sorry.
You want me to start?
Yeah. Please start now.
Thanks. I think, am I audible?
Yes.
Yeah, thanks, Kalpataru. Good afternoon, everyone. So first of all, I would like to thanks the organizer for inviting me for this in this conference. So today I'm going to talk about unconventional superconductivity in lanthanum iron silicon hydride and hafnium vanadium to gallium 4 systems. So we published this work in the physical review research this year, and so I will talk mostly about from this published work. Okay, yeah. So the research team includes there are many people from various groups like from Rutherford Laboratory, Appleton Laboratory. So we have Adroja here, and also from France, Andre Jedfix from USA. And these are all experimentalists, and we also have some theorists. So they did all the theoretical calculations. And I would like to acknowledge Newton Bhava and Nano Mission and DST for funding support. Yeah. So one of the most iconic plots in condensed matter physics, if not all in all of physics, is the phase diagram of high temperature superconductors. Like this is the phase diagram for high TC2 plates, and this is the ionic type superconductors, and these are heavy fermion systems. As the diagram depicts the various electronic phases of high temperature superconducting materials as a function of temperature and doping. that is the addition of atoms that contribute charge carriers. Parent compound of iron-based superconductors are usually metal, unlike the cuprates, but similarly to cuprates are ordered antiferromagnetically that often termed as a spin density wave. And the superconductivity emerges upon either hole or electron doping. The superconductivity emerges from when the antiferromagnetic state disappears or diminished by carrier doping, or maybe structural modification under some external pressure or via chemical pressure or via isovalent substitution. So let me first, so here I summarize the superconducting parameters like superconducting gap and pairing symmetry of several classes of unconventional superconductors, starting from iron-based superconductors and chromium-based superconductors, cage-type superconductor, and non-centrosymmetric superconductor, and heavy fermion superconductor. So it is very interesting to note that some of the compound shows S-wave superconductor, and some of other shows B-wave type superconductors. And in case of this newly discovered iron-based superconductor like 1144 series, it has multiple nodal gap. So there is in different classes the superconducting gap structure is different. So there is no universal classes like for conventional BCS type superconductors. So various research groups measure these gap values and this symmetry using various techniques like RPS and tunnel diode and mu-SR measurement, also from STM measurements. Okay. So here actually, so what we are interested in new kind of unconventional superconductors and also to study the superconducting gap structure by means of mu-SR or tunnel diode or maybe neutron using neutron scattering and neutron deflection studies. So the first compound I would like to discuss about is lanthanum iron silicon hydride. So iron-based superconductors provide an unprecedented playground for the investigations of high temperature superconductivity. These systems belongs to a huge family of compounds recurrently display many key features. The search of novel iron-based superconductors has been naturally extended to several iron X, where X is the group 4 elements like carbon, silicon, germanium, tin, lead, etc. And then particularly for searching new materials, those are non-toxic, like absence of arsenic or selenite compound. So thus the magnesium iron germanium compound has found that this compound has isostructural and isoelectronics with lithium iron arsenic compound, but displaying no superconductivity. So this compound is probably more strongly correlated than lithium iron arsenic sample, since it has a large magnetic moment compared to lithium iron arsenic. By the same argument, it is probably less correlated than the iron selenite compound. And thus correlation effects are unlikely to be responsible for the absence of superconductivity in these systems. Okay, and an important conclusion was that the magnetic exchange interactions in this case are ferromagnetic, while those in case of lithium iron arsenic, anti-magnetic correlations are antiferromagnetic. So another compound people discovered is yttrium iron germanium. yttrium iron to germanium 2. So it shows some superconductivity around 2 Kelvin, but there is this is a intensively debated material. Its electronic structure, though its electronic structure is similar to that of calcium, iron, arsenic in the collapsed tetragonal phase, but with significant fold doping, this led to the speculation about a connection between superconductivity in yttrium iron germanium and the collapsed phase of the extremely hold of potassium iron arsenic. Furthermore, Wang et al. Recently found that yttrium iron germanium to be close to a magnetic instability, and the X-ray absorption and photoemission experiment shows that strong spin fluctuation and moderate correlation effect in this material. On the other hand, hydrogen substitution has been proven to be a particularly interesting route to induce superconductivity in this system, especially the carrier doping limit of the original fluorine substitution in lanthanum iron arsenic oxygen has been suppressed with hydrogen, thus revealing a two-dome superconductivity together with a second magnetic phase transition. Okay, so from structural point of view, they have iron or arsenic layers in which the iron atom forms a square lattice and sandwich between the rare earth lattices, and this leads to a quasi two-dimensional multi-band Fermi surface that mainly originated from the iron 3D orbitals. Okay, so these features, what they suggest? So all these features suggest that S plus minus wave superconducting gap symmetry in case of iron-based superconductor with in presence of spin fluctuating pairing. So this superconductivity can be induced by carrier doping resulting from either chemical substitution or physical pressure. Okay. From a more methodological point of view, one can say that the electronic band structure and magnetic phase orders found in iron-based superconductor can be reasonably well described by means of density functional theory-based calculation, as the electronic correlations often relatively weak in these materials. So here actually we studied this compound, lanthanum iron silicon hydrogen compound using muon spin relaxations and density functional theoretical calculations. Okay, so it is very interesting to see that instead of iron selenite building blocks, so we have iron silicon building blocks in this case, and this resistivity versus temperature graph clearly shows a superconducting transition at around 10 Kelvin. Okay, and we measure the susceptibility and find that the superconducting volume fraction is around 65% at low temperature, and the crystal size the crystal sizes are very tiny crystals, which is 26 cross 15 cross 17 micrometer, and the crystal structure is highly anisotropic compared to the lanthanum iron arsenic compound. Okay, but the interesting thing is that this sample has isostructural, isoelectronic, and isomagnetic similar to the 111 family of iron-based superconductors. Okay, so we also studied the structure using X-ray synchrotron. At 15 Kelvin, there's a structural transition from tetragonal to orthorhombic phase. Okay, sorry. And the resistivity at So the resistivity data in the metallic state follows the normal Fermi liquid type behavior. So we studied the orthorhombic distortion in presence of pressure. So from this data, it's clear that the orthorhombic distortion disappears at around 9.4 GPa, but it again re-emerges at if we increase the pressure, it re-emerges around 12.7 gigapascal. Okay, so this feature is also similar to the iron-based superconductors. We also studied the pressure dependence of the superconducting transition TC, and the TC disappears around 15 GPa pressure. But the interesting thing is that if you increase the pressure, like in this case, the orthorhombic distortion, but we didn't see any means appearance of TC at high pressures. So our theoretical collaborators, so they did the density functional calculations, and after that they calculated the energy differences and effective magnetic moment for the different states, like different model like checkerboard model and means FM model, double strip antiferromagnetic and single strip antiferromagnetic models. But it is interesting to note that the single strip antiferromagnetic model always gives the minimum energy. So we can say that the ground state of the system is single strip antiferromagnetic. So we did a NEOSAR experiment, transfer field NEOSAR experiment, to determine the superconductor magnetic penetration depth as a function of temperature, especially the how does it looks like, the graph looks like. The bold the circular circle represent the experimental data points, and there are many lines dotted or solid lines. Those all are represent the fits using the D wave, anisotropic S wave, isotopic S wave model, and multi-gap nodal and multi-gap isotopic models. But we find that both the multi-gap model like nodal and isotopic models gives the best fit, but the isotopic, but the multi-gap nodal fit gives the minimum values of goodness of fit, and so we conclude that the nodal two-gap superconducting gap symmetry in this sample. Okay, so we also did the tunnel diode experiment, and we also observed the power load behavior at low temperature. This is similar to the NEOSAR experiment, whatever we observed from the similar. Yeah, so it's matches with our NEOSAR result, and we conclude that there is a presence of line node in the superconducting gap structure. So we also calculated the band structure using DFT theory. So and multiple Fermi bands crossing the Fermi surface and Fermi level, and the from the band structure, the main conclusion is that it's metallic in nature and dominated by the 3D orbitals, and this multiband characters, the Fermi surface looks very similar to the iron-based superconductor, but the main difference is here in this part. This part is absent in case of iron-based superconductors, the central belly part. Okay, so we also studied this sample using isotopes of hydrogen. the inelastic Newton scattering data to find the spin resonance energy. And so these are the inelastic Newton scattering data at 5.2 Kelvin and 20 Kelvin, means below and above the superconducting transition at 15 MeV data. But we find that the signature, we find something here in this around 1 MeV or 3 MeV. We find some peaks, but this is not very clear. This might be possible that at 5.2 Kelvin the superconducting volume fraction is less. So our future plan is to measure this inelastic Newton scattering using more high resolution spectrometer and down to millikelvin or maybe at least 1.2 Kelvin. Okay. Kalpataru, how much time I have it?
You have 6
Hello?
minutes. 6 minutes. Hello?
Okay.
6.
Yeah, six
Yeah.
minutes. Okay, yeah. So the next sample is hafnium, vanadium to gallium 4. Okay, so this after the discovery of the leaf space compound hafnium, vanadium 2, with TC at 8 Kelvin is not very clear from this figure, but it's TC around 8 Kelvin. So we started exploring hafnium, vanadium systems, and we choose these systems like 1, 2, 4 systems. So there are many compounds you can see from this. There are many compounds formed in this structure like centrosymmetric tetragonal I4 MKH like structure. But these systems are relatively new, and this is the only one compound. This is the first compound which shows superconducting transition at 3.9 Kelvin. Okay, so and there is no other compound in this family which shows superconducting transition. Some compounds shows magnetic properties, but these are relatively new systems. Okay, so you can see from the resistivity data, we have a sharp drop at 3.9 Kelvin, and the superconducting volume fraction is found to be around 65% at 2.5 Kelvin. Okay. And also resistivity shows linear behavior, means metallic behavior. Okay. The interesting point we observed is that the lower critical field value significantly deviates from the BCS signatures. Here in this graph you can see that. So this motivates us to investigate this material using MESR. Okay, so these are the transverse field MESR time dependent asymmetry spectra, and we have fitted this spectra and calculated the superconducting order parameter as a function of temperature. So these circle represent experimental data, and these are fits using different models. Here also, it is very interesting to note that we have multi-gap superconductivity with we have fitted the best fit is obtained using S+DOM model. The first one with isotopic S-wave gap, and other one is nodal gap. And the values of isotopic gap is 6.27, so which is larger compared to the BCS gap 3.53. So this suggests that strong coupling superconductivity in this system. And this is the zero field asymmetry spectra below and above the superconducting transition. And we have fitted this spectra using exponentially decaying Kubotiabi function and plotted the relaxation rate as a function of temperature. And it is clear that the relaxation rate decreases with increasing temperature. So this suggests that the presence of spin fluctuation in this system. Okay, so we have also calculated longitudinal, means measured the longitudinal MUSR to check whether any impurity present in our systems or what are the values of the internal magnetic field in this system. So we find that, so if we apply a very small tiny magnetic field like 100 Gauss, then we have a full recovery of the polarization, neon asymmetry. So in case of magnetically impure means if there is any magnetic impurity present in the system, or in case of magnetically ordered system, we generally observe a drop in the asymmetry here and or a very large internal field. In this case, the internal field is below, I think, 50 Gauss. Also, here we plotted the Umira plot, and we find that our system like hafnium, vanadium to gallium 4 is very close to the line where the cuprates and nictide superconductor and heavy fermion superconductors lies. Okay. So these all experimental observations suggest unconventional superconductivity in this system. Because we also did band structure calculations and also find that multiple distinct band crossing the Fermi level, which supports our two-gap behavior observed in MUSR experiment, and the dominating means states at the vanadium states near the Fermi level. Okay, so these I think I have almost finished. So the further studies is that the specific features of the electronic band structure of iron, lanthanum, iron, silicon, hydrogen suggest a prominent role of the hole pockets, and accordingly a D-wave superconducting state or multi-gap superconducting state. The outline, this outlines an analogy to the overdoped behavior of the previously iron-based superconductor that is expected to motivate further studies. And for the hafnium sample, several compounds in this series is not studied yet, so this is a stands out an open avenue and an ideal playground to investigate the nature and driven mechanism of unconventional superconducting states. Okay, thank you.
Okay, thank you, Amitabh. So you are well in the time. So now we'll ask if anybody has questions. So please, if you have any questions, please ask to Amitabh. Okay, so maybe I'll ask one question I have. So this lanthanum iron silicon hydride you are talking about. Okay.
Yes. Yes.
The correlation is very weak. That's what you are saying. Is this a quantitative statement, or you have means qualitative statement, or you have some DFT calculation to show that this is the correlation is very weak?
Yeah, I think yeah. So this we did detailed DFT calculations, but I am sorry that I don't know the exact means how they did it and how they find the correlation. But yeah, so we do observe weak correlation effect in these systems, and
okay. Okay, so we are saying that they have done some means DFT calculation to quantify the correlation. Okay.
Yes, yeah.
But it's nothing mentioned what TU and what is the...
Yeah, it's not mentioned in this slide. Yes, I'm sorry about that. But yeah, so that's why actually they used the DFT. Otherwise, I think they might have used another technique to calculate all these things, isn't it?
Yeah. Yeah. Okay, maybe we have still time for another 2-3 questions, but let's see. Anybody? Okay, so you can ask your question, Tirupati.
Okay, yeah. Amitabh, thanks for the nice talk. So in the slide only, I something just immediately sparked. So you have a very large, on this in the previous slide. I mean,
sorry?
The slide that you had when I started the question, maybe slide before? Yes.
This one?
Here the large, large, the Fermi surface, is this whole pocket or electron pocket? It's a whole pocket, isn't it?
Yes, yeah.
So does it
That
have
is.
any significant contribution to the superconductivity?
This part
Yeah.
actually, I think, from this part, this whole pocket, I think, so this arises, I think it has some effect in the superconductivity. I think it arises from the vanadium, if I'm not wrong actually. So, but I guess it has some. Uh,
Okay. So, but you are getting superconductivity on what orbital? Iron orbitals or vanadium
The
orbitals?
vanadium, yeah, so in this case, this is, yeah, iron 3D orbitals, yes. Yeah.
Iron 3D, right? If this whole pocket is from vanadium,
No, it's not vanadium, definitely. There's no
There's no
vanadium here.
vanadium here.
Yeah, the
okay, yeah.
vanadium is the other one actually, other sample, yeah.
No, my interest is,
Yeah,
on this particular one.
yeah,
Because
okay.
this large hole pocket is actually destroying the Fermi surface nesting. The famous theories that many people talked about it. In the case of iron pnictides, I think you know it very well.
Yeah,
The Fermi, as you show, the nesting vector in one of
yeah,
your, upper, yeah, the between
yeah,
Iron,
your
iron based one.
iron
yeah,
based
yeah,
ones.
yeah, yeah.
Yeah, the bottom, yeah, the second one. I think these are from somebody else, isn't it? Or your results
Yes,
only?
yeah, it's just somebody else, yes, yeah.
Yes, there I see a nesting vector. It's perfect nesting, and some theories say because of this nesting you have superconductivity. But then when you come to the this large hole pocket, your nesting is being destroyed or maybe getting reduced, isn't it?
Yeah, yeah, you can see from this one actually, nesting is still there here, but
Okay,
that belly part gets elongated.
okay,
This might be due to the possibility, like in this case, actually, we have in iron-based case, we have S plus minus pairing symmetry. But
yes,
in this case, we have a small, tiny nodal line gap also.
okay,
So that actually it would be interesting to check this by RPS measurement. Yeah, if it is possible. Yeah. So that actually we might plan later. Yeah.
okay. You do RPS also.
Yeah, so that actually, no, I don't do RPS, but
Okay,
actually it would be interesting to study the Fermi surface because this is just the calculations, okay?
yes, yes, yeah,
So, yeah, so as we have single crystals, but those are very tiny. I'm not sure how much, what is the exact dimension we require for the RPS, but
Uh,
anyway, that one can
tiny in
check
the
it.
sense what is the size?
Size is here I mentioned this is the size. Okay, so we have
Okay,
two types of
micrometer.
single crystal
Yeah.
micrometer ranges here.
Okay. Beam will be around of the same order, so I don't know. Synchrotron beam is almost the
Ah,
same order,
okay.
so 100 by 200 micrometer. So I don't know. You may miss it
Yeah.
for our questions. Yeah. Thank you.
Thanks.
Okay, so now we're done with this talk. So let's thank Amitabh once again.
Yeah.
And
Thank you, Kalpataru. Yeah.
yeah, then we'll move to the next talk. Next talk is by
So I'm stop.
yeah, stop sharing.
Ending my.
Yeah, So the next talk is by Dr. Hessling, the editor of JPCM. So Dr. Hessling, are you here?
Yes, hello.
Yeah, so can you please share your screen so then you can start. So you have one hour. So do you like to answer the questions in between or in the end? Because this is 1 hour talk, so we can depend if somebody wants to ask a question, can we interrupt you?
Yes, I welcome questions. I think it would be easiest if we save them till the end. So you can either comment on them in the chat or make a note of them and ask them at the end.
Okay, then you can start. So I'll remind you around 45 to 50 minutes.
Yes, brilliant. Originally, the session I had was only half an hour, so I probably will be able to go slightly over that, but there should be plenty of time for questions.
Yeah, yes, yeah.
Just start sharing my presentation.
Yes, yeah.
Okay, just to check.
Amita, oh yeah, now I can see your screen.
Wonderful.
Yeah.
Okay. Well, hello everyone. Thank you for joining us here on this online conference. I will be talking today on an introduction to reviewing. My name is Jane Hesling. I work at the Institute of Physics Publishing as an editor on several journals, including the Journal of Physics Condensed Matter. There we go. These are some of the topics I will be discussing in the presentation. I'll give you a bit of an introduction to the Institute of Physics Publishing, kind of peer review and what it actually is. There's several different types of peer reviews that are available. The peer review that we run at IOP Publishing, and then kind of looking for, on your perspective, why you should review and how you can become a reviewer. And then an insight from us on what we are looking for in reviewers and what you should check for as a reviewer in the articles you've been asked to review. Then some look into writing your reports, things to consider such as ethical concerns, conflict of interests, confidentiality, and then also some of the things that are being done to recognize the work of reviewers. And we'll round up with some kind of top tips. So the Institute of Physics Publishing, we are actually a wholly owned publishing subsidiary of the Institute of Physics, which is a charity that works in the promotion of physics and physicists across the world. I'll give a brief introduction to them in a moment as well. And all of the profits that we make at IOP Publishing go back to the Institute of Physics to fund their activities. So we are a society publisher. We are embedded in the community we serve, and our mission is to deliver impact, recognition, and value to the scientific community. We have over 300 staff worldwide. Our main office is in Bristol, in England, where I am currently based, although working from home at the moment. We publish over 80 science journals, all with a base focus in physics, but a very kind of broad range of different topics within and related to physics. We also have an ebooks program and award-winning science journalism, including Physics World, which if you haven't seen before, I'd really recommend you can go online and have a look at some of the issues. Very interesting work they write up. Anything you would like to find out further about IOP Publishing, please go to iopscience.iop.org and there will be further information there. So just a little bit about the Institute of Physics. It's a leading scientific society which has been promoting physics and physicists since 1874. There are over 50,000 members worldwide. If you're not already a member of the Institute of Physics, then please do go and look into becoming a member. It's offered from students right up to professors, and their headquarters are based in London. They've just had a new building open for them. And their mission is to advance physics research, its application and education globally. So they engage with policymakers, schools, universities, and even just the general public to develop a greater awareness and understanding of physics. And as I mentioned already, the majority of their funding actually comes from IOP Publishing and the work we do. If you would like any more information on the Institute of Physics, you can simply go to iop.org. So you can see at IOP Publishing, we are a global company, although our headquarters are in Bristol. We do also have offices in North America, Europe, India, China, Japan, as well as representatives in even more countries. And we work with reviewers and authors from around the world. As I mentioned, we have more than 80 titles. Many of them are partner with organizations or society journals. We have our kind of full journal of physics series, which is now 50 years old and counting. And you can see from our publishing portfolio, we have the core of physics within all of our journals, but they range from applied astronomy to plasma, medical, biophysics, materials, engineering, nanophysics. We cover a very wide range of different topics within our publishing portfolio. So we're going to move on now to peer review and what it is. Hopefully, most of you will be aware that peer review is a process whereby experts in the field assess an academic paper before recommending whether or not it should be published. And we recognize this as a vital part of publishing. It really is a critical filter. There are millions of research papers that are written every year. Because it also gives the scientific community and the public a reliable indicator on what's to be believed. If the paper has been peer reviewed, they know it's been seen and recommended to accept by experts. But it also gives the authors feedback. It's an important way for the authors to be able to improve their paper. It's a very rare case when a paper is submitted in a form ready to be published. And it actually also helps us within IOP publishing, so we know what we should be accepting to publish and what we should be rejecting. There are many different types of peer review, actually, some of you which you may already be aware. So the majority of IOP journals are currently run on single blind, which is where the authors don't know who the reviewer is, but the reviewer knows who the authors are. And we have actually recently just announced that we will be switching the majority of the IOP publishing in journals to double blind over the next year. Double blind is when the reviewers of the paper don't know the identity of the authors, and the authors don't know the identity of the reviewers still. And one of the main reasons for doing this is we want to reduce any possible potential biases and focus on the work that's actually being submitted. There are also open reviews where the names of the reviews are disclosed to the authors. This isn't one that we offer at IOP currently. Transparent peer review, where the peer review reports are published with the article. This is actually something we've begun trialing at IOP Publishing. There's also collaborative review. This is one where the reviewers interact with each other, so the reviewers know who each other are, and they can look at each other's reports, either during review or immediately afterwards, and it's a more kind of collaborative final report that is given. There is also the option for post-publication peer review. So an author would simply publish their paper as is, and then it is open for comments on the published version, which may then be updated. And again, this isn't one that we offer at IOP Publishing. So, as I said, most of our journals operate to single blind. This is historically the normal for physics journals, but we have actually for several years already been running double blind options on several of our express titles. And this has proved to be popular with about 30% uptake, particularly with authors from developing countries, which might perceive some sort of conscious or unconscious bias against them in single blind review, which is why we have now made the decision to move all of our journals to double blind, still with the option for authors to reveal themselves and continue single blind, but we will be emphasizing that double blind is the preferred option. And as you can see, we're also trialing some transparent peer review on 3 of our titles, 2 of which are fully open access. This is the case where referees and authors can opt in to have their reports published alongside the article, though referees can still remain anonymous if they wish, and it's a case where both authors and the reviewers have to agree for the reports to be published for this to happen. So this is an ongoing trial, and we're just kind of waiting to see what the outcome is. It's very interesting. So here is just an overview of the peer review process. A paper is submitted and it goes for pre-referee reviewing checks, which is done by the internal editorial staff. This is where we will check a manuscript is in scope for the journal, it's been submitted to and is suitable, has the level of significance and novelty that is needed. We also do any kind of plagiarism screenings with Authenticate. And if all of these checks are passed, we can then send it out for peer review. When we send a paper out for peer review, we will invite reviewers to report, and we require 2 referee reports that are in agreement before being able to make a decision. There is often, occasionally, the need to involve the editorial board, such as a preliminary check on certain manuscripts or adjudications between 2 reports if they disagree. We will also go to the board if we feel a manuscript is becoming delayed in peer review to try and make sure we can get a decision to the authors as soon as possible. And once we have received enough clear and good reviews and recommendations on the manuscript, we are then able to make a decision. Very rarely there is an accept straight away to publish decision. The more likely outcomes are either to revise the manuscript where it's sent back to the authors to look at the reviewer recommendations and then resubmit the manuscript, or that we have to reject the manuscript as it is not suitable for the journal. If we have sent the paper back to the authors to be revised, they will hopefully take into account all of the reviewer recommendations and suggestions. We then ask them to provide a point-by-point feedback for the reviewers, so when they resubmit, we can go back to the original reviewers and ask for their recommendations based upon the resubmitted revised manuscript. And once that has been assessed, maybe a few rounds of the revised process is needed. Hopefully the manuscript will be able to be accepted and then published. And on several of our journals, we have accepted manuscripts, which will be loaded online within 24 hours of being accepted, with then a kind of properly formatted article published officially later on. It can be the case, of course, even after revisions, that a manuscript is found to still not be suitable and has to be rejected, but that is less likely than at the initial first decision stage. So this is obviously a lot of work for reviewers, and you may be asking, well, why would you bother to review? There are several reasons. One is a very simple quid pro quo. If you're writing articles and having them submitted to journals that will need reviewers to look at them and make recommendations, then we would hope that you would want to be able to do the same for other authors when they submit their papers. It's an important process because it helps validate and improve other people's research. It is also nice because you get to stay up to date and at the forefront of your field. You're seeing these papers before they're even published. It does also help reviewers to gain recognition of the work they're doing, and it does help your career. There are several points in your career where it is beneficial to show that you are an active reviewer in the community. And we regularly solicit feedback from authors and reviewers as part of our continuous drive to improve our services for both authors and reviewers. We've gathered here some of the feedback that we've received most recently in the last year or two. We noticed that there is a strong emphasis on improving the author's work. This is what authors really look for. So do keep this in mind when you review manuscripts. Keep your comments constructive and make recommendations to the authors. If the result is a rejection, the author still greatly appreciates suggestions on how to improve their work. Some of the best ones is it's rigorous and honest evaluation. So that the referees tell the authors what is the weaknesses and strengths of my paper and how to improve my paper, like remove the weaknesses. I think it's easily accepted that most authors don't think their papers are going to be perfect straight away, so having this kind of feedback is incredibly helpful. We also, authors recognize the importance of peer review for the broader scientific community in making research reproducible and improving the quality of published work. Peer review is the gateway of scientific quality and reproducibility. Researchers need to know what results they can trust, and one of the best systems we have to do that is with peer review. So hopefully you are considering, if you are not already, on becoming a reviewer. So it may be that a journal invites you to review, or you can actually also contact the journal and volunteer. This you can just go by going to the journal homepage. There will be a contact email address or even a form to fill out where you can go straight away and enter your information to volunteer as a reviewer. When you get a direct invitation from the journal, there are several things that we really want you to consider before agreeing. So, do you have the necessary subject expertise? Are you the right person to review this paper? Are you able to meet the deadline that's set? Do you have any conflicts of interest with the authors? And will you be able to review a revised version? So some of these have, kind of caveats to them. If you don't think you're able to meet the deadline, but you will still be able to do it in a reasonable time, then please contact the journal. Do contact us and ask for an extension. We understand not every paper can be done in the initial deadline that we set, and we are very happy to offer extensions when possible. And also, if you are not able to review an article yourself, but you have a colleague or someone you know who may be suitable, please also do suggest them. It not only helps us with that particular manuscript, but it helps us expand our referee pool and finding suitable reviewers to go to. And a peer-suggested reviewer is always incredibly helpful. And yeah, it's important to know, though, if you have any conflict of interest, obviously, then you may not be suitable as a reviewer. So a bit of insight from our side and what we are looking for in a reviewer. We want reviewers to have the expert knowledge. We want to know that we are getting the right reviewers for the papers. We look for reliability and timely reviews. We also will only try and invite you if you're actually available to report. We don't want to waste your time either. If you have already reviewed for an IOP journal, we do keep a kind of a record of your previous reports and the quality of your reports. And we also want you to remain impartial, which is why we ask you to consider any conflict of interest. We have a large online database of reviewers, which includes their subjects expertise, their author history, and reviewing history. And if someone has been invited in the last month, we try not to invite them again because we don't want to overwork you. We also rate, as I said, the quality of your review reports. So if someone consistently provides a biased or poor reports, then we simply stop using them. But if you are providing excellent quality reports in a timely manner, then we'll be more likely to ask you to review again if you're available. And as I said, we also consider author suggestions. So authors, when they submit a paper, there is a section where they can recommend reviewers, and we will take that into account as well. Making sure, obviously, that there aren't any potential conflicts of interests. So it's important that you keep your research interests up to date so that we can make sure we're inviting you to the most relevant papers. If you moved into a new area of research, or expanded your research areas, do please go in and update your research interests so that we are aware of the best papers to invite you for. So, before you start, make sure you have the required access to the publisher's peer review system. Different publishers may use different systems. We at IP Publishing use Scholar One. Make sure you can access the article and any supplementary information. When you're initially invited to review, you will only be sent the abstract and not the full manuscript. You will only have access to the full manuscript once you have agreed to review. Also have a look at what format the review will take. Different journals, different peer review systems will have different feedback forms and ways of uploading your review. And do go and read the reviewer guidelines for your journals. We have plenty of information at IOP Science for helping reviewers when you are writing, and each journal may have some specific guidelines as well. So it's always very helpful to go to a journal and have a look at their reviewer guidelines. And remember, if you have any questions, please do just get in touch with us. We will always try and help where we possibly can. So, once you have agreed to be a reviewer, these are some of the things that we would ask you to check. So the first thing is read the article fully. Look at all of the figures and the tables, and then you'll be able to decide if the article is understandable and actually correct. You can then assess what the main research question is being addressed in this paper. It will help you look at the article and make sure it actually matches the scope of the journal that they have submitted to. Can you assess the main? Are they novel and important enough for the journal? Do they fill a gap in the research literature? Keep in mind that each journal has different levels of novelty and importance for their papers that they want to publish. So also ask, what is the context of the article relating to previously published work? Have they shown where this research has come from? And are the author's claims sufficiently supported by their research? Have they actually been able to show what they said they have? So assessing the article. This is kind of a guideline of how we suggest you go through the article. Start with the introduction. The introduction should establish the background to the study, describe the main goals and advances, give a brief overview of the methods. It should also start setting the work in context of previous research and cite all relevant and up-to-date references. So this is where the majority of the references will be cited as in the introduction. The methods should give enough information about what the authors did to allow the reproduction of the results. This is a very important part of the methods. Can someone else read this paper and be able to get the same results? Were the techniques used the most appropriate? Is the data correctly interpreted, and does it support the calculations? So is the data actually showing what the authors are saying it's showing? It's also helpful to check if there are any mathematical errors, as this is one of the most commonly common needs for a corrigendum later on after publication, as there was a minor mistake in one of the mathematical equations. Then you move on through the paper to the results and the discussions. This is where the author should be explaining the main findings and the results. They should be showing the significance and the impact of the results. They can also then be comparing their results with other published previous work. And it's also useful to look out if there is any discussion on the limitations of the study. Most work is not going to be completely all-encompassing. There will be some limitations. Do the authors mention it? After this, normally will come the conclusion. So this is where there should be a summary of the major points and findings. The authors should be here highlighting the novelty and significance of their work, and for you to check whether it is sufficient for the journal they are trying to publish in. Again, keeping in mind that every journal has different levels required for novelty and significance. Are the conclusions appropriate, or do they overreach? Have the authors fairly surmised their work? Also look out here if the authors mention any future work planned following the findings that they have published, are proposing in this paper. So when you're assessing the article, these are the things we actually suggest that you do at the end. Look at the abstract and the title. So revisit the abstract once you have read the entire article. This is where the author should be summarizing the whole paper in one paragraph, normally fewer than 300 words. Does the abstract sufficiently explain the key results and findings? This is one of the first things people read when they're looking at the paper, so you want to make sure the authors have clearly surmised what the article is. It's also very helpful to actually look at the title. Is it clear and easy to understand? Is it going to be useful when searching for key terms on when you look it up online, which is how the majority of papers are found nowadays? And also we suggest it doesn't contain any acronyms. So if it contains an acronym that would need defining in the paper, it's better to suggest that they actually use the full term. There are also other things we ask you to consider. The scientific rigor. Is the article actually understandable? Is the work sufficiently correct and robust? Are the mathematics or statistics correct? Has the author made reference to the most appropriate work? Are the scientific arguments accurate and consistent with the results presented? And are there any unsupported claims? So scientific rigor is one of the most important parts we ask authors to meet, and reviewers to check that the authors are meeting the standards needed for the journal. We then ask reviewers to consider the novelty and relevance. So is the work original? Does it actually contain new materials or new results? Is it actually the case that parts of the paper have been published before? Is this paper actually just an incremental advance on previous work? Again, I would emphasize that you check the journal guidelines when making these assessments. Different journals can have very wildly different levels of novelty and impact requirements. So please gauge it on what journal you're reviewing for. But it's also helpful to look at, is the work interesting? How relevant is the work to the researchers in your field? Would you be actually interested in reading this paper? Is the research important, and do the authors actually explain why it's important? It's important that papers clearly show the importance of what their work is. And then finally, we also ask you to check for presentation and languages. I want to emphasize that it is okay to give feedback about the quality of language, particularly if it hinders readers' understanding of the paper. But don't spend too much time worrying about the copy editing and formatting. We have internal production editors who would handle this post-acceptance. So certain aspects we ask you to consider is the paper an appropriate length for its content. So keep in mind the article type and check it against the journal guidelines. If the authors are submitting a letter, we would expect that to be much shorter and concise as opposed to a topical review article, which would be much longer. So also do check that the figures and the tables are clear and are well designed. Can you actually make out what the figures are trying to say? Are the captions clear and informative? As this is another area that when looking for papers, you will often look at the abstract and the figures before deciding to read the entire paper. But then do also make sure the text is clear and concise. And as I said, is the language good enough? It is perfectly fine to suggest that it may need a fluent English speaker to look at the revised manuscript before it is resubmitted. But yes, don't get bogged down in trying to correct all of the spelling or grammatical mistakes in a manuscript. You can simply let us know that they exist, and we will then be able to ask the authors to revise the manuscript and indeed also look at it post acceptance before it is published. Apologies if you can hear my people. There are also other important things to consider. Author misconduct. Please let us know as soon as possible if you suspect any of the following issues. If you suspect that there is plagiarism, which is the substantial replication without attributing of significant elements of the document published by other authors. Basically, if the authors have copied someone else's work and pasted it into their paper, we need to know. But there is also self-plagiarism, which the authors are reusing identical or nearly identical portions of their own previous work, again, without acknowledging they have done so. There are obviously certain parts, technical descriptors for things and equations that have to be reproduced. It's difficult for those to be rewritten. But if they are simply, again, copying and pasting their own work, that is still a form of plagiarism and something that we need to be informed about. You may also come across the fact that it's a parallel submission. So we occasionally do have reviews coming back to us and saying, I have been invited to review this paper on another journal, which is still under active consideration. And this is an ethical issue, as it is not acceptable to submit the same manuscript to several journals at once. So please do inform us of that if you are made aware of it. And very importantly, if you believe there is any fabrication or falsification or even misrepresentation of data or results, please let us know about that as soon as you become aware of it. We do check all submitted articles for plagiarism and self-plagiarism using Authenticate, as I previously mentioned, but it is still very useful for reviewers to watch out for these. And any alarm bells that ring, please let us know. So moving on to writing your report. You've now read the article and taken all of these points into consideration. So we suggest you start with the most important information, an overall summary. This makes it clear that you have read and understood the paper, and then you can follow on with your more detailed feedback. Please be constructive. You can comment on the strengths of the paper as well as what needs to be improved. It's also very helpful to number your points, as this makes it easier when the authors address them and write their point-by-point response. We ask you, of course, to be professional and polite. Do not make any personal or political comments. Remember that the authors are people at the other end of the paper as well. Please be thorough and specific with any criticism you give. It's not helpful just to say that a paper is bad. It's more constructive to explain why and points that the authors can take to improve their paper. We also ask that you make a clear recommendation to both us, the editors, and the authors. And it's okay if you think the recommendation should be rejected. Don't be afraid to say reject. We do provide a confidential comments to the editors section. So if you don't feel comfortable saying something directly to the authors, you can make the comments directly to the editors instead, which won't necessarily be passed on to the authors. And as we said, please make your feedback constructive. The authors want an opportunity to improve their work. Even if the outcome is a reject from this journal, hopefully they'll be able to improve their work and possibly submit elsewhere. We ask that you give your honest opinion. You don't have to play nice. If you want to give some criticism, we just ask it's constructive. We also, as I said, clearly discuss any changes that you recommend. It helps the authors understand why you have asked for these changes. If you think that there are references that should be included that haven't been, please do mention those. As we said, there's no need for you to correct the English unless the science is unclear, and then it would be helpful to make a more scientifically correct suggestion. We do also ask that you don't give away your identity As I said, we currently run single blind and we'll be moving to double blind, which means that we do not want the reviewer's identity revealed. And we ask also for quality ratings on the rigor, quality, significance and clarity before you submit the report. And it's always a good idea to think about what would you like to receive as an author from a reviewer, and try and reach that level of feedback for when you are acting as a reviewer. So, what happens next? After you've submitted your review, you will receive a confirmation email. Your report will be assessed by the internal editors or the editorial team, and the editors will then be able to make a first decision based on your report along with the other reviewer reports received. The outcomes could either be an accept without further amendments, but this is very rare. Most likely we will ask the authors to revise the paper based upon your and other reviewers' recommendations. Or it may be that we have received recommendations that the paper is not suitable and we would have to reject the paper. As previously mentioned, if the reviewers disagree, we will go to a third-party adjudicator, most often a board member, to assess the paper, the reports already given, and give an authoritative recommendation on what decision should be made. We do, most journals will actually tell you what our decision is as well. So, the revised manuscripts. You may be asked to review a revised version depending on the extent of revisions you requested. So, most often, if you're asking for changes after the author has revised the manuscript and sent the resubmission back, we will go back to the same reviewers and ask them to check that the authors have actually made sufficient changes. We ask the authors to submit their point-by-point response to your comments, and this will be made available to you as a reviewer. So please consider, have the authors adequately addressed your previous concerns? Do remember that it is still okay to suggest rejection at this stage if you think the response is unsatisfactory. And after either it's one revised manuscript or maybe a few rounds of going back to the authors, we will be able to have a final decision of accept or reject, which will be made by the editorial team. So moving on to some other considerations. So conflict of interest. Please consider that you might have, you are a close colleague of the author, or someone who has helped the authors with their work. Also, you could be conflict of interest if you're a direct competitor of the author, or if you think that you might be in a position to exploit the author's work. It's fine to decline to review for this reason. Please just let us know, because in fact one of the available drop-down options is decline conflict of interest. And we really appreciate that you declare any conflict of interest at the invitation stage to avoid problems later on. So we say, please make us aware of any conflict of interest as soon as it is possible. You can simply decline, or you can get in touch with the editorial team. It's important to mention as well, with another possible ethical concern, is that we consider it unethical for reviewers to suggest that the authors cite the reviewers' papers excessively. We consider about 3 papers from the reviewer own published work to be acceptable, but if you start suggesting more than 3 of your own papers, then we would start to consider this to be unethical. Please also consider confidentiality. Any paper that is sent for review is considered confidential until published. When you agree to review, we consider that you have agreed to this confidentiality. So please do not discuss the paper with others. If you feel you need a second opinion from someone else to review the paper, then please check with the journal first. We strongly say that you must not make use or cite a paper until it has been formally published. And if you have any printed copies, please discard them after you have finished your review and a final decision has been made. We want authors to to feel confident that their results will not be misused or misappropriated when going through peer review. And this is a strong emphasis on the reviewers to behave in an ethical way. So moving on to some recognition for reviewers. You've seen all of the hard work that it is that a reviewer has to do when peer reviewing a manuscript. And so we are dedicated to try and recognize this hard work and the reviewers. So we have partnered with Publons, which is a service that enables reviewers to track, verify, and showcase their peer review contributions. Don't worry, there's full anonymity is protected this way. It is completely free to academics. We've helped verify over 120,000 reviews in our journals through Publons, crediting more than 20,500 reviewers for their work. For more information, you can go to publons.com and be able to sign up there for recognition if you haven't done already. You can connect this through your ORCID account, and if you do not already have an ORCID account, I will strongly suggest now that you go and create one. We ask all submitting corresponding authors to have an ORCID account, and it will help you as reviewers as well. See, we've done this because our surveys have indicated that academics want institutions such as IIT Publishing and other publishers to do more to recognize the contribution that reviewers make to science, because we wouldn't be able to have such confidence in work being published without our reviewers in the peer review system. At IIT, we also have our reviewer awards. We now run the reviewer awards where our top reviewers for our journals are awarded and publicly acknowledged. We do this by judging the quality, the number of reviews that you're able to complete in a year, and the timeliness of your reviews. So, please write good reviews and accept as much as you can to review. Hopefully, we'll be able to highlight you with one of our reviewer awards. In 2018, we had over 1,200 winners with over 30 journals awarding prizes for our best individual reviewer of the year as well. So I'm just going to move on to our final kind of top tips. So do ask for an extension if you don't think you'll be able to make the deadline. It is fine to ask for an extension. It helps us know that you want to report, you just need a bit more time. Do make any potential conflicts of interest known as soon as possible. If you don't state them straight away, it can lead to problems later on. Please do suggest other experts that might be able to help if you aren't able to review yourself. It's incredibly helpful for us in the editorial team when you do. Please make sure you check the journal guidelines when you make your assessments. Each journal will have a different scope, novelty and impact requirements, so do check the journal individually. Please make your feedback as constructive as possible, even if the outcome is reject, because particularly with a reject manuscript, the authors may be really wanting to improve their paper. Be thorough and specific with your feedback. Using evidence to justify your recommendations is very helpful. It's helpful for authors to understand why you are making a recommendation. Please do watch out for any potential cases of misconduct, including plagiarism, which is also including self-plagiarism and parallel submissions, and let the editorial and journal staff know as soon as possible. And please, we really encourage you to claim recognition for the work you do through Publons and ORCID. And then these are things we don't want you to do. So please don't get bogged down with copy editing and formatting. Providing the article is understandable and readable, that is more valuable for the reviewer to focus on the content. We will be able to fix the copy editing and formatting later. Please also don't forget to mention what you liked about the article as well. If you've got some positive feedback from the authors, that is always gratefully received. But also we say, please don't recommend additional work beyond the scope of the article. You can mention something that you think may be interesting for further work, but you cannot expect the authors to rewrite their paper if it's beyond the scope of what they've submitted. And as previously mentioned, please don't use the review to promote your own work. It's perfectly fine to recommend some of your own articles if they are relevant, but we do keep an eye that people don't try and just send a list of their own papers to get published and up their citations. And also, please don't be rude or personal or political in your comments. We ask that you remain professional and remember that the authors will be asked to do the same to reviewers as well. And also, please don't share or cite the article prior to its publication, as we have asked you to into the confidentiality of the peer review system. So thank you very much. I hope you found this useful and insightful. If there are any questions, I will be very happy to answer them. I will finish sharing my screen so you can see me as I answer any questions.
Okay, thank you, Hesling. So let's see if somebody has some questions. Please ask your questions. Okay. Unmute yourself and ask your questions, please.
Hi, Jen. This is Krishnan. You had a question?
Yeah, please.
Exactly at what stage would you ask somebody to take up reviewing? Is it at the early stage of their PhD or a bit later, or at what stage do you look for this?
We are happy to accept PhD students to review articles, as they're often experts in those particular areas. So from PhD students upwards, really, we would count as suitable reviewers.
Okay, thank you.
So Jen, I also have one question.
Yeah, please.
Yes.
So, like, for being a reviewer, one should be applying for it, or generally that PRB or PRL, they just like send a paper for review. We don't have to apply.
Yeah. So if there is a particular journal that you would like to be a reviewer for, but you haven't previously been invited, we would recommend that you contact that journal and ask to be considered as a reviewer. So you can be added to the kind of reviewer pool and then invited to the most next kind of relevant articles. If you've already been invited to that journal to review, you can probably appreciate that you're a part of the reviewer pool and will be invited to an appropriate article.
Okay, thank you.
Okay, next question, please. If anybody has some questions, please.
If you do ever have any questions then that you don't want to ask now, please feel free to contact IOP Publishing or specific journals, and we'll be happy to answer your questions there as well.
Okay, that will be good also. If there are no questions, let's thank Dr. Jene Hesling for this beautiful talk. Thank you. Then we have, let's say, 10 minutes for the next talk. Manojan, should we go ahead with the talk or should we wait for another 10 minutes?
Go ahead. Please go ahead.
Okay. So the next speaker is Tapas. So Tapas, you are around? Tapas.
Yeah, I am around.
Yeah, so please share your screen and let's start.
Okay. So my video quality is not that good, so I think
you can switch off your video quality. No, not a problem. Only share your screen. That's what.
Okay. Can you see that?
Yeah, we can see your screen. Yeah, perfect. So you have 15 minutes, but you can take another 2 to 3 minutes. But I will remind you in 10-12 minutes. Okay.
Okay. Thank you, Professor.
Yeah.
Okay. Hello, everyone. today I'm going to talk about this dynamic hysteresis and spinodal instabilities at mode transition in V2O3. Before I'm going to the main talks, I would like to attributes of spinodal instability. From the last century, it is quite well known that we have two kind of phase transition. The first order, where the first derivative is vanishes at the transition point, another is the continuous phase transition or second order phase transition. The second derivative or higher order derivative of free energy vanishes at the transition point. In first order phase transition, latency is been observed, and in some cases, hysteresis is also been observed. Whereas in the continuous phase transitions, the scaling, which is the underlying features of universality, is observed, and critical slowing down, that is relaxation, is very slow at the transition point. Basically, the relaxation time constant diverges at the transition point. And the critical operations is a consequence of fluctuation that always take place at the molecular scale. But at transition point, the correlation length divergence, and hence the susceptibility is divergence, and hence this fluctuation grows, and light will be strongly scattered in this light scattering measurement. So this all the first order as well as the second order phase transition expected to observe with these spinodal instabilities, and it is a new class of transition. We are calling it the zeroth order transition. So why I am calling it zeroth order, I will explain it later. So this is my conclusion of talking. So basically, I will explain at the end of my talk. I can convey you that the zeroth order phase transition actually take place in the real materials. So the idea is I will take a system which shows hysteresis and have some latent heat, which is a basically signature of first order phase transition, and I will demonstrate the divergence of susceptibility in this talk, and which is the signature of this second order phase transition. So let me introduce my group members. Satyaki Kundu is the IPhD student in our lab, and the MA students and these professors, and Dr. Bhaptosh Bansal, our group leader, and my PhD supervisor. And we are recently working with Dr. Srimanta Midda, who has given in the nice talk. And many of these samples, long-range interacting system, shows these kind of features, but I will show some of these candidates. One of these is the metal insulator transition at the NDNO3, V2O3, VO2, and I will demonstrate on the V2O3. And the professor A.K. Raychaudhury's group has already got this similar behavior, this enlargement of fluctuation at this transition point, similar to us and in the recent work in archive. So, and this is also this all these other materials, spin crossover, CDW, and all these kind of transitions should show some kind of critical signature. This is the expected, I expect. And this magnetic materials, Whistler alloy, set memory, and other things. Okay, I will not go into the details. Let me come to our system, where the V2O3, and it's been studied for 70 years. We took it as just a model system, and it shows a abrupt phase transition around 150 Kelvin, and it has a large thermal hysteresis. So before understanding the zeroth order transition, we have to understand the hysteretic transition first. And I will explain in terms of the spin system. That at h is equal to 0, system is in upspin state. As we decreases the field from h is equal to 0 to some critical field, the free energy will tilt, and then the system will stuck in the spin up state, and the up to the point where this point of inflection is reached, and there is no the fluctuation, the barrier is completely vanishes, and phase will transform from one phase to another through a rolling down a hill. And if we decreases again, the phase will stay in the downspin state, and if we now increase the spin, it will stay in the downspin state up to this positive critical field, where this phase will again transform by a rolling down a hill. So now just to complete this hysteresis cycle, I have drawn this free energy, and the final state and the first state are the same. And this convention is called the delay convention. However, in normal first order phase transition, it doesn't show hysteresis, and that physics is basically captured by Maxwell construction, and it says the system always stay in the global minima, and free energy is always convex. No hysteresis and phase transformation is take place by the nucleation and growth process. So now, if we have some kind of fluctuation, system can transform or sufficient amount of fluctuation that the system can transform this barrier, activation barrier, then system will transform here, not the here. But if the phase transition, if the thermal fluctuation doesn't take part into the phase transition business, then the phase can persist right up to the spinodal point where this barrier is completely vanishes and phase will transform through a rolling down a hill. So this kind of transition is called this athermal transition. So here the barrier is completely vanished, and you can see that here the free energy itself is discontinuous, not the first order derivative of this free energy. That's why we are calling it the zeroth order, because free energy itself discontinuous as the transition point. So now at this spinodal point, first derivative is always zero, and the second derivative, as this is the point of inflection, so it is also zero. So there is basically this two well converted to a one single well, and hence the susceptibility, which is the inverse of second derivative, is diverges. So which is the usual case for second order phase transition at critical temperature. First derivative and second derivative of free energy is vanishes, and this susceptibility is diverges at this critical temperature. So now we are talking about this athermal transition in a thermal driven phase transition. So of course it sounds crazy because we are basically driving the temperature, but we are getting this thermal fluctuation doesn't take part into the phase transition business. But this athermal transition has been studied extensively in the structural phase transition. And I will talk about this dynamic hysteresis scaling experiment. And this differential we fabricate a differential thermal analysis technique, and we took the two equivalent substrate which is connected to a thermal bath, and a sample is mounted on a substrate A, and we are changing this thermal receiver temperature in this RAMS fashion, and now we are measuring the temperature difference of these two substrate A, TA minus TB with respect to the reference substrate B. And during this transition, the sample will absorb or release latent heat, and then one would get this peak and dip in this temperature difference, and this peak point are the transition temperature of this transition temperature. So if we increases the now ramp rate from 0.5 Kelvin to 16 Kelvin per minute, and then I will get that this transition temperature is shifted. And we did the resistance measurement, and there is also that this area of the hysteresis is shifted with this rate of change of temperature. So this shift in transition temperature follow a scaling relationship with this ramp rate, and this exponent 2/3 is the mean field exponent of spinodal transition. So 2/3 is at least universal in its mean field concept. So this is the so now I will shortly summarize the talk, that the scaling suggests some kind of criticality, and 2/3 suggests the spinodal transition. Now I will come to the next experiment, which is called critical slowing down. And the experimental technique is that we are starting from very low temperature and quickly quench to this transition region and wait for some time. And this is the temperature profile of this measurement. And now we are looking this resistance evolution with time, and this is also called the phase ordering measurement. Now we are converted this resistance time graph to the order parameter versus time graph through a percolating model conversion, and we did it for the heating and cooling, and the circle are the measurement data point, and these feet are the exponential feet, where tau is the relaxation time of this measure relaxation time of this phase ordering measurement. Now we plotted the tau varices different quench temperature, and we have got a clear signature of diverging time scale, relaxation time scale at the spinodal temperature, both for heating and cooling. So this is a signature of slowing down, or phase signature of slowing down in the first order phase transition. Similar measurement done by our lab member Satyaki. He have done this resistance noise fluctuation measurement, and plotted this autocorrelation time varies as temperature, and it also shows that the autocorrelation time constant peaks at this transition temperature. These two measurements shows the critical slowing down observed at this first order phase transition. And now I will shortly discuss about this noise measurement. So this picture shows that this retained resistance noise fluctuation taken at different positions, the insulator, the transition region, and this metallic region. And you can see that during this transition region, fluctuation is enhanced. And these enhancements also is observed for the cooling cases, and we converted this resistance fluctuation to the order parameter fluctuation, and we plotted in terms of this this variance, and this shows that this variance is fixed at this transition temperature both for heating and cooling. And this is basically the signature of the divergence of susceptibility itself. So it's a kind of critical opalescence which has been observed in this experimental system. So now I will summarize by saying that we have started with hysteretic material, hysteresis hysteretic transition material, which has a latent rate of 15 TC and shows a dynamic scaling. And this exponent is the prediction of spinodal transition 2/3. And we also experimentally got this critical slowing down and critical opalescence at the first order phase transition. So the two signature also showing that this is a kind of criticality observed in the first order phase transition. So that's why I'm saying that the zeroth order phase transition actually been taken place in the real material. So thank you for your kind attention.
Okay, thank you, Tapas. So let's see if somebody has some questions. Okay, so if there are no questions, let's thank Tapas again. So thank you, Tapas.
Okay, thank you.
Thank you. Now may I request Professor Priya Mahadavan to announce something. Are you here, Professor Priya?
I was just trying to unmute myself.
Yeah.
So on behalf of the organizers, Kalpataru, I'd like to thank you for chairing the session. Yeah. And
announcement for the moving to the session 1 or something.
So may I request all of you all to move to session 1 at the end. It's still going on, and at the end we will have a feedback. We'd like to have a feedback of about the conference from all of you, as well as there's going to be a vote of thanks thing. So please move there. Thank you.
Maybe some of one of the host can put a slide here so that anybody log in here can they can move to the next session or something, because this session ends much before than the expected.
Sure. Okay. Yeah, sure. Yeah, Devlina, can you just put a slide there, please? Thanks.
Yes, ma'am.
Just put a slide that please move to parallel session 1.
Okay.
Yeah, thanks.
Thank you, Priya.
Yeah, thanks.
Let's move to the first session. All of you. Kaltaru.
Yeah.
Please join.
Okay.